Water is filled up to a height h in a beaker of radius capital R as shown in the figure. The density of water is rho. The surface tension of water is capital T and the atmospheric pressure is capital P naught. Consider a vertical section ABCD of the water column through a diameter of the beaker. The force on water on one side of this section by water on the other side of this section has magnitude mod 2 P naught RH plus pi r squared rho gh minus 2 RT, 2 P naught RH plus r rho gh squared minus 2 RT, P naught pi r squared plus r rho gh squared minus 2 RT, P naught pi r squared plus r rho gh squared plus 2 RT. Observe the last term in every option. Okay, that is 2r into capital T, and you know that is actually the surface tension, right? That is actually the surface tension. And because this surface tension being force per unit length acting on either side of an imaginary line, in this case that line is AB, diameter being 2r, it's 2r into T, so that is clear. Okay, now let us draw an enlarged view of that section. Okay, let's draw an enlarged view. Suppose this is AB. Okay, suppose this is AB. Okay, suppose this is AB. Now you know that because pressure is going to increase with depth. Okay, because the pressure is going to increase with depth. Okay, the net force which will act, let's say, on some area here will be greater than net force that acts here. Okay, because of the increase in the pressure, right? And what how will we calculate that pressure? That pressure will be atmospheric pressure plus rho change. Okay, is it clear? But because we want to find the net force, okay, we want to find the net force, we have to consider integration here. Okay, we have to make use of integration. Please try to understand why integration is being used. Because on every area, okay, the deeper it is from AB or from the surface, greater will be the pressure there and therefore the force. Okay, so I'll write that point first. Point 1. As P varies with H, okay, regions of ABCD close to CD will have greater force than regions close to AB. Okay, that's first point. Number two, force due to pressure. Okay, force due to pressure and due to surface tension. Okay, due to surface tension will be opposite in direction. Okay, surface tension will try to pull it, pressure will try to push it back, right? So if we are considering whichever surface we consider, that's fine. So if we are considering the direction of pressure like this, or the force due to pressure, then we have to consider the force due to surface tension in this direction. So obviously the surface tension will have a negative sign. Okay, surface tension will have a negative sign. Okay, due to pressure. Okay, so that is clear. Well, actually the pressure is preventing the motion of the fluid through ABCD, right? And hence you understood why it is in the direction opposite to surface tension, because surface tension will kind of tries to pull it. Okay? Okay. Now, how do we start integrating? The force due to surface tension is constant, but the force due to pressure variation is different. So what we will consider is, we'll consider horizontal strips. Okay, let's do that. Let's consider horizontal strips. Okay, now when we consider that horizontal strip, we will assume that it is at a depth x. Let x be our variable of integration. Okay, so suppose this is that strip. Okay, strip we consider depth x, depth is x, and thickness is dx. Okay, thickness is dx. Okay, and this will be x. Now let us calculate the area. Okay, let us calculate the area. What will be area of the strip? Area is length into breadth. Thickness is a dx, and what is the width? Width is 2r, right? 2r is the diameter, so this will be 2r. Area will be 2r dx. Okay. Now what will be the force acting? Now this is an elementary force. Okay, elementary in terms of not in terms of the fundamental forces, elementary in terms of the force which is acting on that particular segment. What is the force? Let's call it df. This force will be pressure into area. Do you agree? Pressure into area, so that will be 2 capital R dx into P. Okay, now how can we calculate P? It is given to us that atmospheric pressure is P naught. Okay, and assuming the incompressibility of water, we can assume that density of water remains constant. So P will be P naught plus rho g. We usually say H, but here because that H is varying, let us take the depth x there. So P naught plus rho gx into 2r dx. That is the force acting on that particular strip. So what will be net force? Net force will be obtained by integrating this. Okay, integrating this with appropriate limits. Okay, limits force, and those limits will be on x from 0 to bottom is h. Okay, now okay, let's write it systematically so that no term is missed. Into 2 capital R dx. Firstly, let us integrate P naught 2 capital R. So that will be P naught 2 capital R into x, and we can happily replace that x by h. And what will we do for rho gx? Let us write rho g and 2 capital R separately, and x's integral is x squared by 2, so it will be h squared by 2. Okay, so it will be 2 P naught capital R h plus rho g capital R h squared, and so this is due to pressure. Okay, so net force or combined force, I should say combined force, it will be equal to this minus 2 capital RT due to surface tension and mod. See if we have that option. Okay, let's see if we have that option. Okay, pi is not there, right? So A is not there. 2 P naught RH is there, so C is also not there. 2 P naught RH plus rho G R H squared, rho G R, okay, minus, yes. So option B is right. Okay, option B is right. So this is a problem where they have combined fluid statics, that is hydrostatics, pressure and surface tension. Okay, well, I included it for two reasons. First, I wanted to emphasize that don't expect that one single concept or formula will be at work. And secondly, it has integration, so you should understand how integration is to be carried out, because if we take it as an integration problem, then integration is not difficult, okay, but how we convert that situation into that integration problem, that is important. So